In this video, we'll continue our discussion of section 7.6. This is over translation theorems. This is our second translation theorem, so it says if it has a Laplace transform, so just know that big F of S is the Laplace of F of t, and then we have some constant A. So this is where that last video kind of left off, is we're going to take the Laplace of a Heaviside function. When I take the Laplace of a Heaviside function, whatever this A is becomes this power. All right, so notice the negative, so be careful. Whatever, if this is t plus 4, that means this is an e to the 4s. It's going to look the same because they both have negative. And then this part, if you take a look, this is just the Laplace of the function f. Let's derive it, then we'll get some examples to make it a little easier for you. So we're taking the Laplace of f t minus a times h t minus a. We're just going to run through the definition here. All right, this is 0 to infinity of e to the negative st, negative st, times f t minus a times h t minus a. Now remember from that last video, what this thing does is moves my function over to a. So it kills, the Heaviside function kills f up until a. It's a 0. So what that means is if I split this up, 0 to a of this junk, this part is going to be a 0, right? Because that doesn't get turned on until a. Go back and look at that other video. It doesn't turn until it gets on. And then I can do a to infinity, e to the negative st, and then I can just throw this function here. I don't need Heaviside. Heaviside already was taken care of because Heaviside just turns it off until I get to a. But if this starts at a, then it doesn't matter. Heaviside is a 1. I don't need to include it. But I do need to keep the t minus a. All right. That first integral, it's a 0, right? So we're good there. We're just going to work here. Let's let u equal t minus a. This also gives us t. T is u plus a. We also have du. Du is dt. Nice and easy. All right. So replacing our u's, right? If I'm plugging in a into my u, a minus a is 0. Infinity minus a is still just going to be infinity. And then I get e to the negative, and we're going to replace t. T is u plus a, times the function becomes f of u du. Okay, we can break this up. This is in with respect to u, so this e becomes e negative su, e negative sa. I can pull out e to the negative sa because it doesn't have any u's. So we get e to the negative su times fu du. Okay, so this is e to the negative sa times, notice this is the Laplace of f. We used u instead of t, but remember, when we're talking about this variable inside of our integral, it's just a dummy character, meaning I can change it to whatever I wanted. So if you wanted to change those to t's at this point, I guess you could to make yourself feel better, but it would be a little weird since we did this. I probably wouldn't write it, maybe just think about it. All right, so that is that formula. Let's get a few examples in. All right, so here's the application. We have that. Now, I'm going to write this formula down at the top of the page, just so we have it. So the Laplace of f of t minus a times h of t minus a is equal to e to the negative a s times the Laplace of f. All right, so our function here, and it's a little hidden. One thing I want you to notice is this says t minus 3, that has 3 minus t, so I'm going to do some kind of fixing. So I know my function is going to look like, okay, I got 3 minus t to the 5th, and I would really like it to be t minus 3. So I'm going to flip this over by just making a negative. And all that is still to the 5th power. Well, a negative to the 5th power is still negative. So I get negative t minus 3 to the 5th. So this is my function f of x. I'll call x here to help. This is negative x to the 5th. But what they did is they plugged in t minus 3. So we get negative t minus 3 to the 5th. Hopefully you can tell. what I'm trying to show you is this is the function that we are dealing with a t minus 3. All right, so I'm going to rewrite this. This is the Laplace of negative t minus 3 to the 5th times h of t minus 3. This is equal to, now we use the definition up here. It says e to the negative as. Well, a in this case is the 3, so it's going to be a negative 3, so I'm going to have e to the negative 3s times, and then it's just the Laplace of our function. Our function is negative, and we could throw this to be a t, negative t to the 5th. All right, so that gets me a negative. The rule for this from our table is 5 factorial over s to the n plus 1, so we get a 6. Right, this ends up being, we could write it out to be nice and pretty, negative 120 e to the negative 3s over s to the 6th. And you could leave it the line above. I don't care. I just want you to be able to use the theorem. All right. So you do have to match the argument, meaning if the heavy side has a t minus 3, the function itself has to have a t minus 3, so you have to manipulate it in some way. Leading into that, sometimes we have these crazy cases here where the heavy side is t minus pi over 4, while the cosine doesn't even have that in there. So what we're going to do instead is we're going to rewrite this. The Laplace of, and then this is the cosine of, let's do a bracket, 3, and I'm going to replace t with t minus pi over 4. But if I do that and I distribute that, I'm adding a negative 3 pi over 4 in, so I need to add a positive in there to keep it the same. Oh, and I need my heavy side. Okay, so notice this is just e to the negative 4s using the last rule times, we can leave that off, Laplace of cosine of 3t plus 3 pi over 4. Remember the function, the rule itself, I'm going to scroll to the top here. The rule itself says, hey, take this function that has that in there and then add that in, right? And also take the Laplace of that function without the t minus a. So that's what we did there, is we took out this t minus pi over 4, and that's what that left us with. Now, this is going to use some trig. I know everybody's favorite. Oh, that shouldn't be a 4. That should be a pi over 4. Right, it's the, oh, that's because I wrote this wrong. That's where I got that. There we go. Okay, so we are there, and we got e to the negative pi over 4s, and then we need the Laplace of that, but it's not, we don't have any rules for that, so I'm going to use a trig identity. Cosine, it's the sum rule, so cosine of 3t times cosine of 3 pi over 4 minus sine of 3t sine of 3 pi over 4. Some of you guys are like, do I need to know that? Maybe it's a note card thing that you could put down just in case. What I do for a note card, those of you guys that do make note cards, especially for this, you're going to have that table, is I would have a table and write down on a note card everything that you use as you work out your homework. That's how I would do it, is if I use this trig identity in the homework, then I'm going to write it down, just in case. Okay, so we keep going, e to the negative pi over 4s. And then, so this is, I can go ahead and start taking things out here. Cosine of 3 pi over 4 is negative rad 2 over 2. Cosine of 3t. Oh, we shouldn't drop our Laplace. Oh, that's what I was going to do. Okay, so I'm taking out negative rad 2 over 2 because it's a constant, and then I'm going to take the Laplace of what's left. Minus, okay, this is also radical 2 over 2, but a positive, but that minus will make that. And then I have the Laplace of sine 3t. There we go. All right, so I'm going to factor out the negative rad 2 over 2. e to the negative pi over 4s. And then it's going to be times, okay, the derivative, I want to say derivative, Laplace of cosine 3t is going to be, cosine has the variable on top, cosine, or s over s squared plus 9. The sign there, because I factored out the negative, so it's a plus now. The sign has s squared plus 9, but a on top, where a is 3 from that 9, right? It's the square root. There we go. There is our Laplace transform. All right, we have one more form of this translation theorem, and then we'll get to IVPs. All right, so alternative form of the second translation theorem. The first one is the actual form. The second one says, okay, well, what if I can't get the function in terms of t minus a? Well, if I can't get the function in terms of t minus a, what I can do is treat the beginning the same. I get that. But now I take the Laplace of that function with t plus a inside of it. Okay, let me make sure, let's make sure you understand what that means. So the Laplace of t squared h times t minus 2. So the t minus 2 is the problem here. That's what would be here, which means my function would need to have a t minus 2. Since it doesn't, this form allows me to use that same thing. So I get e to the negative 2s. But instead now I do the Laplace of t plus 2 squared. I just took the t minus 2, and you do the opposite, t plus 2, and you put that inside of the function. Now, the only way around this is to multiply that out. So we get the Laplace of t squared plus 4t plus 4. And we get e to the negative 2s times, okay, this is 2 factorial over s to the third. This is going to be 4 over s squared. And then 4 over s. Those are just using the table, keeping the constants up front. All right, I got another one here for you, 2 more examples, and then we'll work towards IVPs. All right, so we have this. This one's a little easy, harder to see at the beginning, but it's not too bad. All right, so the inverse Laplace. And now we have that e. I'm going to put the e to the negative pi s. This is working backwards now. S squared plus 1. This looks like the right side of the formula up here. So we get e to the negative as. That's going to give me the heavy side. So I'm going to write heavy side t minus pi. I know that. And then it says, okay, whatever this is, right, to go backwards is just going to be that function. So we get sine of, because that's what this is, right? That's sine of t. But we get to put a t minus pi. Just going backwards. I know that's a sine, and then this actually follows that top rule, right? So we are here, and we went there without the L, right? Because now we have the inverse Laplace on the right side. All right, this one is a trig rule. Don't know if you guys will remember it. It's because sine is odd. We get that. And I don't mean odd as in strange. I mean an odd function. All right, I got one more example for you. Not the cleanest one either. And it's going to lead into where we're going with these IVPs. All right, so I have that function there. I am going to split this up. Okay, so we are going to use, I know I have to break up this 1 over s squared, s minus 1. So I am going to use fraction decomposition, a over s minus 1, and then this one's going to feel weird, but it's bs plus c over s squared. All right, so let's go ahead and figure these out. S equals 1. We should multiply first, I guess. I always forget to do that. 1 equals a times s squared times bs plus c times s minus 1. All right, so let s equal 1. We get 1 equals a. That's nice. S equals 0. All right, we get 1 equals s is 0. We get negative c, which tells me c is negative 1. And then we'll do s equals -1. Plugging all this in, we're going to end up with 1 equals 1 plus negative b minus 1 times -2. This leads to, if you work this out, b is -1. Okay, so we have a, b, and c here. So what we're going to do now is we're going to take this and split it up. All right, so that's the inverse Laplace of e to the -2s times 1 over s minus 1 plus the inverse Laplace of e to the -2s times -s minus 1 over s squared. We can break that up. Okay, we can go ahead and go backwards here. This is going to be, now this one's kind of weird. Okay, so we get h t minus 2, that comes from here. And then we're going to get this, the normal is e to the t, right? That's the normal translation. But I have to put t minus 2 in there. So it's e to the t minus 2. Okay. That's what that rule calls for. And then the same thing here, but I'm going to split this up a little bit. Excuse me. All right, we can actually split this up to 1 over s minus 1 over s squared. We still have e to the t minus 2 times h times t minus 2. Plus, okay, that's going to still get that same thing, but we get a 1 plus t. That comes from here. And a minus. All right, that is the heavy side rule. I took the Laplace, inverse Laplaces of what's inside, then I did the heavy side to take count for the e. I can then also put the h's together to leave me with e to the t minus 2 minus t minus 1 times my heavy side. All right, that is it there. We are working towards IVPs. The reason that we went through this whole translation theorem with the heavy side was to eventually take our Laplace of a piecewise function, which is where we're leading next.